Hello all, we are discussing bearing capacity. This is video part 2. In previous video, we have learned different basic of bearing capacity like definitions of gross bearing capacity, net bearing capacity, ultimate bearing capacity, etc. etc. After that, we saw what is actually a bearing capacity is and what are its basics. After that, in this lecture, we are going to particularly learn one theory which is Terzaghi's bearing capacity theory, which is most popular among other theories. Let us move towards that. So let us start with assumptions. First assumption is the footing is long, or we can say L by B ratio is infinite. It means very long. The base of footing is rough. So the base of the footing must be rough. The footing is laid at a shallow depth. It should not be too much deep foundation. It should be at a shallow depth. The load on the footing is vertical and is uniformly distributed. So UDL must be there as well as it should be only vertical. The shear strength of the soil above the base is neglected. So no shear strength is there. It is assumed like that. The soil above the base is replaced with an equivalent surcharge gamma into D. So we are considering it as a surcharge and not having any shear strength. The shear strength of the soil is governed by Mohr-Coulomb equation, which we have learned in previous chapters. So these are basic assumptions by Terzaghi. Carl Terzaghi is known as father of soil mechanics. He has worked enormous amount of work in soil mechanics. Let us understand this equation. This equation is given by Terzaghi for ultimate bearing capacity of a strip footing. Equation is like QU. QU is bearing capacity. C into NC plus gamma into D into NQ plus 0.5 gamma into B into N gamma. Now, C is cohesion here. Gamma, that is unit weight of soil, must be in kilonewton per meter cube. D, depth of the footing. B, breadth of the footing. So you must be having these two data. NC, NQ and N gamma are Terzaghi's bearing capacity factors. They are variable. Variable with what? Angle of shearing resistance phi. So according to phi, it will change. In this figure, you can see Terzaghi assumed something like that. Here, he has assumed a strip foundation, strip footing, and the load is like this. Uniformly distributed load, and it is converted here into one concentrated load. Okay, this is the breadth of the footing, and it is given like this. And here zone 1, 2 and 3 are divided by Terzaghi. How? First zone will be soil wedge under footing, second will be plastic zone and third will be passive zone. According to that, he has derived this theory and this equation. Let us move further. Here NC, NQ and N gamma equations will be like this. NQ is equal to whole square A square upon 2 cos square 45 plus 5 by 2, where A will be e raised to 3 pi by 4 minus 5 by 2 into 10 phi. So this is the factor defined by Terzaghi. Same way, NC is defined as NQ minus 1 cot phi, and N gamma is defined as 10 phi by 2 into Kp by cos square phi minus 1. So these are the formulas given by Terzaghi. You must remember these formulas to understand numericals very well. Furthermore, Terzaghi has given this table. Now, according to phi and general and local shear failure, NC, NQ and gamma values will change. So, if the phi shearing angle of resistance is 0, when phi can be 0? When the soil is pure cohesive, right? So for that, NC, NQ and N gamma is given like this. Same way, if the local shear failure is happening, it is given like this. So same way, according to phi, all values are given. If your angle of shearing resistance, for an example, it is between 0 to 5. Suppose it is 3, then we have to interpolate the values of constants. Let us move further. Equation for local shear failure. For local shear failure, we have understood local general shear failure very well. Now, if phi is less than 29, Terzaghi has proposed one formula and he has told that local shear failure will happen. So, C will be C dash now is equal to 2/3 of C, and phi will be phi dash now, it will be tan inverse minus into 2 by 3 tan phi, and Qu will be 2 by 3 C into Nc dash plus gamma D Nq dash plus 0.5 gamma B into N gamma dash. So this formula will be somewhat modified due to local shear failure. Now, if the phi is greater than 36, then Terzaghi told that it will be a general shear failure. And in case of general shear failure, let us take an example of if phi is equal to 40 degree, then NC, NQ and gamma will be obtained from the table, right, which I have shown previously. If it is a case of local shear failure, if phi is less than 29, let us say phi is 25 degree. For that, phi dash will be tan inverse 2 by 3 tan phi. That is how it comes as 17.27 degree, and by interpolation, NC, NQ and N gamma can be obtained like this. If your phi dash value is 17.27, so you have to interpolate between 15 and 20, right? So here they have interpolated values of 15 and 20 and they have multiplied the values by this, plus they have added some value. This sum value will be of at degree 15. If you see a table as well as this, you will get to know how they have interpolated. Moving on to the next case, if the phi angle is in between 29 and 36, then which failure will happen? Then mixed failure will happen. It will be not exactly a general failure as well as it will not be an exact local shear failure. So it will be a mixture. For that, let us say angle phi is 35. For that, we have to find out phi dash. Phi dash tan inverse into 2 by 3 tan phi. That is, phi is given as 35. So phi dash becomes 25 degree. Now, if it was a local shear, if it was a general shear, I would take one case only. But in this case, I have to consider both of them. So I'll take phi 35 and phi dash 25. For both, values are as shown in this picture. These values are taken from table. NC 57.8, NQ 41.4, and gamma 42.4. Same way NC dash, NQ dash, and gamma dash. Now, what we have to do is we have to take a difference of them. So let us understand the difference. So difference of NC value between both of them, that is 32.6. Difference between NQ values, that is 12.6, and difference between N gamma values, that is 32.3. So these are differences. Now what we have to do is we have to multiply these difference with 6 by 7. Why 6 by 7? For this we have to understand this. We are finding for an angle of 35 degree, right? So I have to understand what is the additional angle after 29. So if I add 6 into 29, it will become 35. So there is a gap of 6 degrees, and total range of variation will be 36 minus 29, that will be a 7. So in denominator it will be always a 7, and in numerator it will change. So here in this case it is 6 by 7. So I have to multiply this difference with 6 by 7, and the original NC dash value, NQ dash value, and N gamma dash value will be added to that. So I will get NC value, NQ value, and N gamma value. These are now singular values for this case only. From that I can calculate Q easily. Now for square footing, Terzaghi has given one formula which is like this: 1.3 CNC plus gamma D NQ plus 0.4 gamma B into n gamma. So it is somewhat changed than the regular one. Circular footing 1.3 C NC plus gamma D into NQ plus 0.3 gamma B into n gamma. And for rectangular footing, it is like this: Q is equal to 1.3 C into NC in bracket 1 plus 0.3 B by L plus gamma D NQ plus zero point 0.5 gamma B into n gamma in bracket 1 minus 0.2 B by L. So these are the formulas which you have to remember. Moving forward, for effect of water table on bearing capacity, Terzaghi has given one more formula, which is this: C into Nc plus gamma 1 D Nq into Rw1 plus 0.5 gamma 2 B into N2 into Rw2. Here Rw1 and Rw2 are reduction factors for water table. So due to getting higher water table, you have to reduce some strength. It is quite understandable. Let us move further. For first case, water table located above the base of the footing. For this case, I have to take Rw1 as 0.5 in bracket 1 plus Zw1 by D and Rw2 as 0.5. Same way, if the case is second one, water table located at a depth below the base of the footing, then Rw1 will be 1 and Rw2 will be 0.51 plus Zw2 upon D. Here people do mistake B and D. So do remember that where you will take breadth and where you will consider depth. And in the third case, if water table located at same depth of the base of the footing, then Rw1 and Rw2 both will be 1 and there will be no reduction in bearing capacity because it will be at the same depth of base of the footing and it will not affect that. Moving forward to one numerical. A footing 2.25 meter square is located at the depth of 1.5 meter and it is in a sand of unit weight 18 kN per meter cube. So it is a sand. The shear strength parameters C is equal to 0 due to sand and phi is 36 degree. Calculate the safe load carried by the footing against complete shear failure. Factor of safety is given as 3. Use Terzaghi's analysis. So you have been told that use Terzaghi's theory. And 3 factors are already given, so you don't have to remember whole table. But the repetitive values should be remembered. So if there is not some data given, you can cover that. NC is given as 65.4, NQ is 49.4, and gamma is 54. So given data, C is 0, gamma 18, B 2.25 and D 1.5. Let us understand that. For square footing, QU is given as 1.3 C into NC plus gamma D NQ plus 0.4 gamma B into N gamma. So values of C, D and B and gamma are given, but what about NC, NQ and N gamma? They are also provided by problem. So we have to put all the things in one formula which you have to remember. And the QU bearing capacity comes out as 2208.6 kN per meter square. So this is my bearing capacity. But here I am told that find safe load carried by the footing. Right? For safe load, you have to find out QNU, which is net ultimate load. Net ultimate load will be given by QU minus gamma into D. So you have to remove surcharge from there. That is how you can get net load. So 2208.6 minus gamma, that is 18, and D depth is given as 1.5. So QNU will be 2181.6 kN per meter square. After that, QNS would be found out. QNS is what? Net safe capacity. So QNU by F, factor of safety, is also given by problem, that is 3. So I am putting that formula QNU by F. So I am getting 727.2 kN per meter square. After this, I have to find out QS, which is safe capacity. Safe capacity will be QNS plus gamma into D. Here I am adding surcharge into this because I want to stay safe, right? So QNS is 7 to 7.2 plus gamma into D, that is 18 into 1.5. So I'm getting QS, safe bearing capacity, as 754.2 kilonewton per meter square. Now this is per meter square capacity, right? If you want to find safe load, that will be in kilonewton, so that I am doing QS, total safe load, will be small qs into its area. So it is per meter square, so I have to consider its area. Area will be 2.25, which is breadth, and it is a square footing. That is how I will take other side as 2.25 only. So area into qs will be my safe load, and it is coming out as 3818.14 kilonewtons. I hope you understand these formulas and numericals. In next video, we will understand more numericals as well as theory. Thank you.